This is a little bit more about the complex conjugate root theorem, which takes a long time to explain, but it really is very, very easy if you just think about it in this sense. When you have a polynomial which only has real coefficients, and that's very important. Real coefficients are things like 5, 10, square root of 3. No imaginary numbers, in other words. As long as your polynomial is real, that means that if there is a solution with an imaginary part, like this guy, see how that has an imaginary part, the 2i? That means there exists another solution, which is the conjugate of the first one. So 5 minus 2i is also a solution. It must be, according to the complex conjugate root theorem. Now, all that's left is to find the polynomial. And to do this, I'm going to write it first in factored form. P of x, that's our polynomial, equals x minus x1 times x minus x2 times x minus x3. So each one of these is x minus the solution. And as many solutions as there are, that's how many factors you have. So if you have 10 solutions for x, you're going to have 10 factors. It's going to be a real doozy. In this case, we have 3. We have to multiply this all out. And what I want to do now is tell you what x minus x1 is. Well, x1 is negative 5, so that means x minus x1 is x plus 5. And x minus x2, follow the negative signs, is going to be x minus 5 minus 2i. And x minus x3, x minus 5 plus 2i. All right, that's factored form. If you put this in as your answer right here, it's going to be wrong because it doesn't want factored form. It wants you to go through the exercise of multiplying this out. And what I want to do is teach you a quick shortcut for actually multiplying this out. It's not as bad as it looks. Think about it this way. You can multiply this in any order you want. And what I want to do is first focus on this multiplication right here, because I'm going to tell you there's a trick to making this easy. Look at this, x minus 5, x minus 5, right? Minus 2i plus 2i. Do you see the difference of squares there? The difference of squares has 3 terms in it. There's one of the terms, the x minus 5, and then the 2i is the other one. So here's what it turns into. If you recognize that shortcut. And feel free to pause the video and think about this a little bit. But this turns into x minus 5 squared minus 2i squared. This is the difference of squares identity, which basically says, here, I'll write it in a little simpler form. Can I not write up here? I can write up here. A minus b times a plus b equals a squared minus b squared. Remember that one? That's what I'm using here. Oh, it went away. Oh, that's weird. Okay. Anyway, rewind the video if you want it again, but that's that trick that I just did here. So I'm going to say the following. This is still x plus 5 on the outside. And the inside of this thing becomes, well, x minus 5 squared is x squared minus 10x plus 25. And then I have that minus 2i squared thing, which is minus 4i squared, which, if you remember what I squared is negative 1. So this becomes plus 4. Okay, and now this is x plus 5 times x squared minus 10x plus 29. That's the trick. That got us through this a little quicker than you might have otherwise. And now all that's left is for you to finish multiplying this out. You could use the box method or whatever method you like and put it in there. I'll leave that as an exercise for you. I just want to wrap up with a couple of notes about the complex conjugate root theorem. So here's what I'm talking about right here. Real polynomials might contain imaginary roots, like this one. Okay, there's a root with an imaginary part here. And that doesn't mean the polynomial is not real. It just means one of the roots of it is imaginary. Now, the restriction is, if you see one root that's imaginary, you know there's going to be another one, right? They come in pairs. So you might have 2 roots that are imaginary. You might have 4 roots that are imaginary. You will not have 3 roots that are imaginary. Because if you did, then the coefficients of your polynomial would not be real. Okay? Now, as soon as you get into imaginary coefficients of a polynomial, which might exist, all that means is the complex conjugate root theorem goes out the window, and you can't do this math that I've been doing here. It's just a different situation. Second note that's important. A polynomial of degree n must have n complex solutions and n complex factors. Now, if you look at this one, you might think, hey, that's not, n is 3, right? It's a degree 3 polynomial, but I only see 2 complex solutions. Well, you're not looking closely enough. All of these solutions are complex. Even -5 is complex. Remember what complex means. It just means a plus bi. Well, you can be a complex number with no imaginary part, right? That's just a real number. So the real part is -5, the imaginary part is 0. It's still a complex number. So keep in mind that complex, the word complex, does not mean imaginary. It just means real parts and imaginary parts. Maybe one of those parts is 0, but basically every number is complex in that it has a real and imaginary part. So a polynomial must have n complex solutions and n complex factors, as long as it is a degree n polynomial.